Welcome all. This lecture is on conformations of cyclohexane. Cyclohexane is the most stable alicyclic ring system. If it exists in the planar form, then the angle between any two CC bonds will be 120 degrees. The normal tetrahedral bond angle is 109.5 degrees, but here this tetrahedral carbon is having the bond angle. The sp3 hybridized carbon here is having a bond angle of 120 degrees. So there is a considerable deviation from the normal tetrahedral bond angle. As a result, this molecule will have an angle strain. The angle strain between these two CC bonds will be the normal tetrahedral bond angle 109.5 minus the actual bond angle 120 degrees divided by 2. That gives 5.25 degrees. So like this, there is angle strain between all the carbon-carbon bonds. So this angle strain increases the energy of the molecule. That is why cyclohexane does not exist in this planar form. Suppose if it is existing in the planar form, every carbon will have a CH bond above the plane and CH bond below the plane. CH above this plane in this carbon and the CH bond above the plane in this carbon will be eclipsing. The CH bond here and the CH bond here also will be eclipsing. Like that, there will be 12 eclipsing interactions in the planar form of cyclohexane. That is why there is considerable angle strain in the planar form. There are 12 eclipsing interactions. In order to avoid the angle strain and the energy rise due to the eclipsing interactions, cyclohexane exists with the non-planar conformations which are called the puckered ring structures. The different non-planar conformations of cyclohexane are chair form, half chair, twisted boat and boat form. One chair form can be converted into another chair form by lifting this down carbon up and up carbon down. In this chair form, in the planar structure of cyclohexane, all the 6 carbon atoms were in a plane, whereas in this chair form, the non-planar conformer, the puckered ring structure, these 4 carbon atoms in the middle are in the same plane and one carbon is below the plane, the other one is above the plane. We can convert this chair form into another chair form by lifting this down carbon up and this up carbon down. First of all, when we lift this down carbon up gradually, it becomes a half chair. And still when we lift it up, it becomes a twisted boat and then it becomes boat. Now we have to bring this up carbon down. When we bring this up carbon down, once again it becomes a twisted boat and then it is converted to another half chair and then it becomes another chair form. Let us see how it happens. We can visualize the interconversion of the different conformers of cyclohexane. Now from the chair form, this down carbon is slightly lifted up. Now it has become half chair. Now still it is being lifted. It goes through the twisted boat into the boat form. Now this is the boat form of cyclohexane. It becomes half chair. Still When this carbon is brought down, it becomes another chair. So these are the different conformers of cyclohexane: chair, half chair and boat. One chair is converted to another chair. This is called ring flipping. And during this ring flipping, all the axial bonds are converted to equatorial bonds and equatorial are converted to axial. Actually, this rounded bond in this previous chair form was in the equatorial position. Now that has become axial bond. Chair form of cyclohexane is the most stable conformation. In this most stable conformation, the bond angle between any two CC bonds is approximately 109 degrees, which is the tetrahedral bond angle, which is closer to the tetrahedral bond angle. And in this chair form, in the Newman projection, we can see all the CH bonds are staggered and there is no eclipsing interactions. So in the planar form, there is huge angular strain present. That angle strain is absent in the chair form. In the planar form, there were 12 CH-CH eclipsing interactions, and those eclipsing interactions are absent here as all CH bonds are staggered. Since the angle strain is not there, no eclipsing interaction is there, this chair form becomes more stable. And this chair form of cyclohexane is achiral, since there is a plane of symmetry present in this molecule. A plane connecting 1,4 is the plane of symmetry, which can divide the molecules into two equal halves. So this chair form of cyclohexane is achiral, but there are 6 Gauss-butane interactions present in this chair form. You can just see carbon number 2, 3, 4, 5. You can just consider this like a butane. And with respect to bond C3C4 bond, these two bonds are having Gauss interaction. Just like that, 1, 2, 3, 4. This part of the molecule can be considered like N-butane, and here with respect to the bond between C2, C3, these two bonds will have the Gauss interactions. So this 1, 2, 3, 4, 2, 3, 4, 5, like that you can find 6 Gauss-butane interactions. Every Gauss-butane interaction increases the energy of the molecule by 0.9 kilocalories per mole. Since there are 6 Gauss-butane interactions, the energy of the molecule is raised by 5.4 kilocalories per mole. And apart from this energy raising Gauss-butane interaction, there is another repulsive interaction present in cyclohexane, that is the 1,3 diaxial repulsive interaction. These two axial bonds will repel each other. As long as these are hydrogens, the repulsion becomes negligible. Instead of hydrogen, if you have some other bulky groups, this 1,3 diaxial repulsion will raise the energy of the molecule considerably. In the chair form of cyclohexane, there is a principal axis of rotation present at the center of the ring, and all the CH bonds which are parallel to this principal axis are called axial bonds. All the axial bonds are shown with red lines here, and these are all parallel to this principal axis of rotation. And there are 6 other bonds present in all the 6 carbon atoms which are shown with the blue color. They are all directed away from this axis and at an angle of 109.5 degrees. And these are all called equatorial bonds. In each carbon atom of this chair form, there is an axial CH bond and an equatorial CH bond. All the CH bonds in the adjacent carbon atoms are staggered with respect to each other, and hence there is no eclipsing interaction present in this chair form. So in the planar form of cyclohexane we have seen there are 12 eclipsing interactions present, but in the chair form all the CH bonds in the adjacent carbon atoms are staggered, and hence there is no eclipsing interaction, and hence this chair conformation is more stable than the planar form. In fact, this is the most stable conformation among all the possible conformations of cyclohexane.